23. When you have tangent secant squared, that tangent secant is 3x. Three x quantity squared is 9x squared. Most of you guys probably just wrote 3x squared. And that's where you're done goofed. So now in this case, you don't have any constants. What I mean by that is any number without variables. So you have to set one side equal to 0. So I'm going to take everything on the right, move it to the left. Subtract them both over. You get 5x squared minus 20x, and that's 0. Which means here, in order to solve for x or figure out what's going on, you have to just take out GCFs. 5x squared and 20x, what do they have in common? 5x. 5x, good. So you factor out the 5x. Excuse me. You get x minus 4. Now you have your two terms that you can set equal to 0. One of which is ridiculously simple. 5x equals 0, and x minus 4 is 0. All right, it's real tough brain power here. 5 times what is 0? 0. Good. And the other one is 4. Can I have a segment length that equals 0? So I say, tosse ole, senor 0. Make sure your name's right. I won't tell you the sum. No, just last night, so it's all I'm worried about. Then we got a whole bunch of stuff to go over with you. Have their own bits and pieces to them. And if you think about some of the stuff that were in each of the sections, they kept showing up all throughout. Same thing with things that we've done earlier in the school year. How many times do we have to use Pythagorean theorem while we're in a triangle or in a circle here? Oh, a lot. How many times did I relate back to how some of these theorems and stuff work because of congruent triangles? A lot. So there's so much intertwined material from previous stuff in geometry, but then again, it also utilizes more algebra. So yes, this was a giant bit of information. So what I want to do today is kind of go over the first 4 sections. That one section that's up there that I wrote 10-5, remember that was the section out of chapter 11. That was the 11.4, that was the arc length. Why this chapter on circles doesn't include anything about circumference and arc length is beyond me. So that's why we've been bringing into this chapter, oh geez, ever since we started this book, 9-10 years ago, I think, somewhere in that neighborhood. So what I've made for you guys, I made this the other day. I made a packet that's got probably 2 to 3 problems per section built throughout it, and I'm going to try and get through about half of the material that's in that thing today. Check it tomorrow. Go through the other half of the material tomorrow, and we test Friday. All right. Now, bear in mind that this is all good review things. I will give you tons and tons of tips and tricks. So make sure you're writing as much of this down as possible. So one of the first things we did in the beginning of this section, obviously, was to define a bunch of stuff about circles. Okay? Watch your phone. You guys are your damn phones. I don't know why. You have attention spans and gnats. Squirrel. In this case here, the dot in the middle of the circle denotes the what of the circle. Okay. Well, what else do we call it? Center. The center of the circle. And you're right, Mackie. If this was labeled A, we'd call it circle A. Okay. Not literally circle the letter A. Now, when we did that, we defined circles at a set of points that are all equidistant to the center. That's how circles are created. This also had a name. Center out. What is that? Radius. The radius is from the center out. The radius is from the center out of a circle. Now, within a circle, what do you know about all the radii? All the radii in the circle are the same. So all radii of a circle are always congruent. Okay? Now, what makes circles congruent are the radii. If one circle has a radius of 5, and a different circle has a radius of 5, those circles would be congruent just because the radiuses are the same. After we talked about radius, we talked about something called a chord. Chords were one of those segments that are in a circle that always have endpoints on the circle. Chords create arcs. Okay? The endpoints of chords lie on the circle, which create an arc. We all right with that? The most famous chord of them all is the The diameter is the most famous chord of them all. The diameter cuts a circle in half. Okay? A diameter cuts a circle in half. It still is a chord because it's got endpoints on the circle. But what is the diameter made up of? The diameter is equal to 2 radii. That comes into play later on when we talk about circumference. Because remember when we talked about that, it was 2 pi r, pi times diameter. That's where all that stuff becomes interrelated. After you had the diameter, we also then drew in this. It was the secant. The secant was a segment that went through a circle. I think I used the bad analogy of secant destroy, because like an arrow would go through something, it would destroy it.
I think you're right. I remember not laughing. That's good.
Thank you. Anyway, so a secant goes through a circle. And remember, we've used secants later on to talk about angles. We use secants later on to talk about segments and things like that. But it's one of those things that you take for granted of what did it actually mean. It just means it went through a circle. Okay? And then I think the last one was the tangent. And what's fancy about a tangent, if I can even draw it, is that the tangent touches the circle at exactly one spot, and it's always what to a radius? Perpendicular, right? A tangent will always be perpendicular to a radius. All right, so tangents touch the circle at one spot. They are perpendicular to a radius. That was kind of the first group of a lot of the vocabulary that was in the unit. You all right? Just bite your lip or something. Huh? Oh, because you won't look like that, like it bit his tongue or something. After we did that, we started to get more involved within the circle. And we started talking about angles. Remember, sometimes I'll use theta. Theta is okay to use. It's the same thing as you're saying an angle measure. Instead of using x, sometimes you'll see that.
Is it still 10-1 or is
It
it 10-2?
kind of, you're right, I don't. I know that some things, I I know a lot of it blends together. 10-1, 10-2 kind of blend together a little bit. I'm gonna hit a lot of it at the same time. I think we first defined what the angle at the center of a circle was called in 10-1. Remember, it was called a central angle. And that's an angle whose vertex at the center. Okay. The angle who has a vertex at the center, notice that the sides of that angle run into an arc. Okay. Central angle. Angle. Vertex. At. Center. Huh?
That's not an
That's
yeah.
not an at symbol.
Yeah, it is.
No, it's not.
That's a
At
swirl.
symbol is like an A that goes around. Yeah, that is an at symbol.
It's kind of the same thing.
No, what is it even different? You have to draw an A.
Shroud, your look at your face is priceless. Okay. How about this?
Thank you.
Is that better?
Yeah, why are you trying to
No,
be simple?
now there's no center. There's no C.
Suck it up, Buttercup. You'll be fine.
You can't go with the C.
All right. So the central angle is an angle whose center is or vertex lies on the center of the circle. Now, one of the things that we talked about is that this central angle runs into an arc. So we knew that the measure of the angle equals the measure of the arc that it hits. So if that angle measured 86 degrees, what would the arc measure? 86, good. After we talk about central angles, we then talk about what were called inscribed angles. Oh, I just gave it away. What is that called?
That is an inscribed.
It's an inscribed angle. Very good for paying attention. And an inscribed angle was an angle whose vertex was on the circle. Okay. So central angles equal the arc they hit. What did inscribed angles equal? Half the arc they hit. So an inscribed angle equals half the arc. So this angle runs into an arc measure of 86, which makes that inscribed angle how much? 43, very good. Okay. Now, what would this one be? That inscribed angle also has to equal how much? 43. Because remember, the angle will always measure half of whatever arc it hits. So you could have infinite number of angles hitting the same arc, which means you could have a whole bunch of congruent angles. It's perfectly fine. Okay? All right? Now, one of the things I was talking about with fourth hour was sometimes it's not just, find half the angle. Sometimes you have to utilize two parts to solve a problem. And this is where I got with fourth hour today. And they were asking, oh yeah, the definitions, that's not so bad, and angles equal half the arc, the angle equals the arc, things like that.
Oh, see, I was looking way next to house.
And that's what happens. If you're not careful, you make this more difficult than it needs to be. For example, that 94 degrees is what kind of an angle?
Central.
It's a central angle. Do you guys agree that it runs into some arc right here?
Yeah.
Which makes that arc how much? 94. Now working backwards then, doesn't that angle hit that 94? Which means that angle is going to be how much? Half of it. So half of 94 is 47. So it's not that you're just going to say, oh, my angle lies on here and going to give you that. It'll make you take an extra step to get there. Okay? That's all. It just makes you take an extra step. Also in, it's been 10-2 then, when we started talking more and more about arcs, we also talked about the different types of arcs. And there were 3 of them. When we were also in 10-2, we talked about different types of arcs. You had major, minor arcs, and another one that was called a semicircle. What was the difference between major and minor arcs? Right. Major arcs were larger than larger than 180. Minor were smaller than 180. Greater than 180 degrees, smaller than 180 degrees. Remember, these are capped at 360 and 0. We're not going to be talking about arc measures and angle measures that go beyond 360 degrees. We're not going to be talking about arc measures that go below 0 degrees. That's an Algebra 2 topic that talks about how many times you revolve around the circle. That's not for us to worry about for now, okay? That's just multiple revolutions. So you have major arcs, minor arcs. Also, one of the things that helped denote the differences between the two were the number of letters. When you're talking about arcs, remember, it's always shortest distance between 2 points. So if I say arc AC, am I going this way or that way? This way. It's always going to be the shortest distance. So minor arcs generally are 2 letters. Major arcs would be usually 3 letters. Now, it's not to say that it might not be, but more often than not, if you want to think of that, using 2 and 3 letters helps that. That middle letter for a major arc just tells you what direction you're going. You might see a minor arc written as ABC, just because it's just telling you what direction to go. That's all. Just to help clear up any cobwebs on it. But more often than not, minor arcs are just 2 letters. And then a semicircle does what to a circle? Cuts it in half. How many degrees then are on both sides of a semicircle? Now, when you did this stuff, we had you wound up with big picture style problems. You wound up with big picture problems to be able to walk through and figure out all the different angles, central angles and whatnot. You had directions that were written in here. If something that appears to be a diameter, it is. This was allowing you to assume and not make an angle side side out of you and me. Direct. and it also let you guys go through and use vertical angles. Now remember, vertical angles aren't anything that we specifically talked a ton about in this unit, but they show up over and over and over again. Okay. Now, also that shows up a lot here is this idea of supplementary. Supplementary means two angles add up to equal how much? 180. So it appears to me that this is a diameter, which means how much is on this side? Whoa. 110. Which means this appears to be a diameter, which means how much is here? That'd be a 70. This appears to be a diameter, so 70, 30, and what is 180? 80. It's things like that. Just being able to go through a diagram and fill in the blanks prior to trying to answer a whole bunch of questions. Okay? It's just following, I don't want to say following tick marks, but it's just following your arcs around to see how do they match up via diameters and things like that. Okay? If I'm not mistaken, you guys never really had too much of an issue with this stuff. The arcs, because those were pretty clean. Where the wheels tended to fall off at a little bit more with us was probably when we got into arc length. Arc length was that weird section. That was that section that I brought in out of chapter 11. And it's weird that it's in chapter 11 because chapter 11 deals with areas, surface area stuff, but we don't really use circumference with area. So, I don't know. Like I said, ever since I can remember, we've been teaching that section in with the circles because it kind of makes sense to be there. So, arc length is the part of the perimeter. It's part of the perimeter. It's the distance that you walk on a curve. When you walk on a curve, it's longer than walking in a straight line. I mean, think about it when you're on a track. Get my drift. This is the curved portion here. This is the curved portion here. It'd be a lot easier just to run here, hang a left, hang a left, hang a left. You're cutting out this whole curved part, but there would also be cheating. Cheaters never win. So, arc length, you're dealing with a portion of the circumference. Now, like I said a second ago, your circumference is the distance around a circle. The circumference was the distance around a circle, and it had a formula to solve for. The circumference was always equal to twice the radius times pi. But the math etiquette way of writing that is 2 pi r. Variables after that. Now, the other way that we wrote out circumference is that, what's another name for twice your radius? Diameter. So we also wrote this as circumference equals pi times the diameter. They were fine either way. Now, the arc length being a portion of a circle, what you needed to figure out then is how much of this circle was created. Well, that portion of the circle was created by that central angle. Now, there's only 360 degrees in a circle to go to start with. So what all you have to do then is figure out, well, hey, I'm just using so much of the circle. Well, I'm using 20 degrees of the circle. So 20 degrees of the circumference. You're looking at that much of it. So this arc length then was that central angle over 360 times 2 pi r, or we wrote it as angle over 360 times pi times the diameter or we wrote it as angle over 360 times circumference. All three of those were legitimate ways to write out the formula for arc length. Any one of them would have worked. You would choose between one of them depending upon what information they were giving you. And I believe, and this was also the time that I was always telling you guys to leave your answers in terms of pi. And I think that everybody in here, pretty sure, has the calculators that will leave answers in terms of pi for you. So please, you have to remember to bring that with you. Okay? You have to. Otherwise, you're going to not be happy. Please. What's that? Well, you might not be happy
I was
anyway.
quoting
Who? I didn't hear you.
Elf the movie.
Yeah, I know. Well, I didn't hear what you said there.
But I'm not happy. The little dude in Elf. He's the boss man.
Santa?
No. But he's like this tall. He's a midget. He's
He's an elf?
The angry elf.
Yeah, but he's not an elf. He's a businessman.
Yeah.
And he called him an elf. He said, "Oh, you're an angry elf, aren't you?"
Oh, yes, yes. I know who you're talking about now. Yes. Yes, ma'am. I'm sorry, what? I don't know. I haven't decided. Probably not. I don't know. Probably not.
Thank you.
So if I go back to the diagram I had here a second ago, let's say that this was 110 with a radius of 4. Let's say this is 110 with a radius of 4. Remember, what you're doing here, guys, is you're just basically substituting in a whole bunch of information to make it work. So if you're trying to find the arc length in red there, central angle over 360 times 2 times 4 times pi. Well, that becomes 9. 11 times 2, you get 22 pi over 9. And that would be your final answer. No decimals, no nothing. You get that answer. Your calculators will do that for you. 110 fraction bar 360 times 2 times 4 times pi. And it will spit out 22 pi over 9, and you will smile because you should be right. What? Are you trying to mock me now? I'm trying to be supportive and encouraging. Thank you. Kind words from you, Miss Toad. Only because what?
I'm in a good.
I'm glad to hear that you're in a good mood. Air 5.
You're not gonna ask her why she's in a good.
I don't care.
Wait.
Oh, I'm sorry. Okay. All right, Miss Toad, why are you in such a grandiose mood? A what? Okay, well, congratulations.
Thank you.
You're welcome. All right. So a lot of times with this, we were also had to work backwards. Because if you think about with the arc length formulas, there are 3 bits of information. Arc length, radius, angle. Arc length, diameter, angle. Arc length, circumference, angle. So sometimes you're not just solving for the arc length, you could in fact be solving for the radius. You could be solving for the angle. Which means you have to remember how to work backwards. For example, if I take a circle, have a central angle of 60 and an arc length of 15 inches. And I want to know what the radius is. So if I work this one backwards, we start with the circle, we have a central angle, and we know that that's got to be an arc length because the value, or excuse me, the unit of measure, if you will, is in inches or it's feet. As long as it's not degrees, you know it's got to be a length. Okay, it's got to be a length here. So, which of the three formulas for arc length has radius? Well, that was the arc length, angle over 360 times 2 pi r. And again, you'll notice you know two of the three variables. Fill them in. Okay. So, one of two things you can do. Your calculators will multiply out this first chunk in your calculator for you. Okay? They will. So if you put in your calculator fraction bar 60 over 360 times 2 pi, it should say 15 equals 16 pi over 3. It should do that. I believe so.
Yeah.
Okay. Now, when you do that, how do you undo multiplying by pi over 3?
Reciprocal?
Reciprocal. You can divide, but it's easier. I want you guys to break the habit of dividing fractions. I want you to just always to multiply by reciprocals. If you get through that in your brain by saying multiply reciprocals, it's going to help you out tremendously next year, because that's all we talk about. Okay. So that means I got to multiply both sides by 3 over pi. So if I'm doing this with the calculator, it probably will just spit out 45 divided by pi. But if I ask you to round to the nearest hundredth, you would press that double arrow button. If you press the double arrow button, 45 divided by 3, we want almost 16, 15 and a half, somewhere there? 14 and a half?
14, 3, 2, 3, 9, 4, 4, 8.
So it's 14.32?
Yep.
Or you said 329.
3, 2, 3, 2, 3, 9.
3239, thank you.
Okay.
What do you got?
I didn't, no, I'm confused how to put it in here.
Where? Which part?
The pi over 3 times.
This? Oh, all you have to do is make a fraction bar of pi over 3, and then hit to the right button times 15.
Okay.
It'll look just like that. Yeah, I usually put it over 1, that way you guys don't think that something else is going on weird. Okay? And that's where you get your arc length stuff from.
So then 14.32 would be the radius.
Yeah. And then we got into 10.3. 10.3 had everything to do about chords. Ten-3 had everything to do about chords, and basically, I think there were some tandem segments in there too, and I don't know if we'll get time to get to that. We're running a little short here. What happens with chords is that if two chords are congruent with the circle, what do you know about the two arcs that those chords intersect?
They're the same.
Yeah, if the chords are congruent, that means that the arcs that they run into are also congruent. And it also works going the other way. If two arcs are congruent, the chords that create them would also be congruent. Now, the reason why we had congruent chords was because of if you took the center and you drew to the chord, if two chords are equidistant from the center, those chords would be congruent. And the reason that works is because of congruent triangles. Because I could draw in all those guys are radii. All four of those segments in blue would be radii. All four of those segments in blue share the equidistant part here. They're all perpendicular to the sides, which means you have 4 congruent triangles by hypotenuse length. Which means then that all of these pieces, all of those would be the same. There's a lot of congruent triangles. Yeah, there's a lot of congruent, bless you. There's a lot of congruent triangles that come about when you're dealing with stuff like this. Okay? The reason that all of this stuff works goes back to triangles. Okay? Now, the other bit that was in here with the chords, and this is probably the last one we'll be able to get to here, was that if a chord intercepts a diameter, if a chord intercepts a diameter, what does that diameter do to the chord? It splits it in half, and it does what else? What? Yeah. It's a perpendicular bisector. Okay. The other part of this works out to be that a diameter is can be the perpendicular bisector of a chord. Now, I know I went through a ton of material here at a somewhat quick of a pace, but I do have this review pack thing that we made that works out really, really nice. Now, I told this to the other classes, tomorrow afternoon, probably right after school, I will post online a worked out answer guide for this. So that way you can go back and verify your answers. And then you can also check to see how the work was done. So I'll have a fully worked out answer key for this online on the calendar tomorrow after school.
We went over with
What I'd like you guys to be able to do on this one tonight, I'd like you guys to get through the first 20 of them. Okay? I'd like you to get through the first 20 of these. That should not take very long, in all honesty. Most of the problems themselves are pretty quick. All right? The second half of these take a little bit longer. And we'll probably spend a good chunk of time in class talk working through some of the second half of these problems as well, because that's where some of the factoring and things come back into play. Okay? So go through the first 20 of these for tonight. We'll get through the rest of the quick tips and tricks stuff of sections 4, 5, 6, and 7 tomorrow, and we'll go from there. All right? Yay. Back is stiff.